For as long as human beings have existed beneath the night sky, the moon has been there. Silent, distant, unchanging. It hangs above oceans, deserts, forests, and cities. A pale presence that never quite feels part of the earth below it. Across every culture and every era, people have looked up at it and wondered the same quiet questions. What is it? How far away is it really? And perhaps most importantly, could we ever reach it? Long before telescopes, the moon was mythology. It was a god, a spirit, a watcher in the sky. Ancient civilizations built calendars around its phases, tracking its slow transformation from thin crescent to full glowing circle and back again. It governed tides, harvests, rituals, and stories passed down through generations. But for all its influence, it remained unreachable. Even as science began to replace myth, even as astronomers mapped the stars and planets with increasing precision, the moon stayed just out of reach. A nearby world that might as well have been infinite. For centuries, it was a place for imagination more than exploration. And yet, something changed. In the early 20th century, the idea of reaching the moon stopped belonging only to storytellers. Engineers began to sketch it. Mathematicians began to calculate it. Writers began to imagine machines powerful enough to break free from Earth's gravity and travel through the silence between worlds. At first, it seemed impossible. Rocketry was still in its infancy. Early designs were fragile, unstable, and often failed in spectacular ways. The dream of space travel belonged more to fiction than engineering. But slowly, almost quietly, the foundation of something new began to take shape. A few experiments worked. Then a few more. Small successes stacked on top of failures, each one teaching something new about the harsh reality of leaving Earth behind. And beneath it all, the world itself was changing. Nations were advancing quickly through technology and science. War had accelerated innovation in ways no one could have predicted. Rockets, once experimental curiosities, became powerful instruments of engineering and, eventually, competition. What had once been a distant dream was now becoming a question of capability. Could it be done? And if it could, who would be the first? By the mid-20th century, the moon was no longer just a symbol in the sky. It had become a destination, not yet reached, not yet touched, but suddenly, seriously considered. Governments began to invest in programs designed not just to reach orbit, but to go further, to push beyond Earth entirely, to send machines, and eventually people, into the space between worlds. And so began a new kind of race, not across land or sea, but upward, into the sky, into orbit, into the vacuum beyond. It would become one of the most ambitious undertakings in human history, a journey defined by mathematics, engineering, risk, and patience, a story built from thousands of small decisions, countless tests, and an almost unimaginable amount of coordination between people who would never meet, yet worked toward the same distant goal. But before any human could walk on the moon, before any rocket could leave Earth with enough certainty to return, there had to be a beginning, a spark, a first step into the unknown. And that beginning is where our story slowly starts to unfold. Long before the moon became a destination, it was a question, not a place to go, but a problem to think about. For centuries, humanity understood motion on Earth quite well. Things fell, rivers flowed, birds flew through air. But beyond the sky, beyond the reach of wind and weather, there was something different, something quiet. Something that did not behave like anything on the ground, and to reach it would require breaking every familiar rule of movement. The earliest ideas of space travel did not begin in laboratories or engineering firms. They began in thought experiments, simple, almost fragile ideas written by people trying to imagine what might happen if motion could continue beyond the atmosphere. One of the earliest voices was Konstantin Tsiolkovsky, a Russian schoolteacher who spent much of his life quietly developing mathematical ideas about space travel. He worked in isolation, far from the centers of power or industry, writing about rockets long before they existed in any practical form. To him, space was not fantasy. It was physics waiting to be understood. He imagined vehicles that could move beyond Earth not by wings or balloons, but by reaction, by pushing against expelled gas, like a gentle recoil repeated over and over. His equations described how a machine could, in theory, leave the Earth entirely. At the time, these ideas existed mostly on paper. There was no industry to build them, no materials suited for them, no urgency driving them forward. But the math was there, and sometimes that is enough to begin something. Around the same time, in other parts of the world, similar ideas began to appear. In Germany, Hermann Oberth studied rocket motion and wrote about the possibility of spaceflight as something scientifically achievable, not just imagined. In the United States, Robert Goddard quietly experimented with early liquid-fueled rockets, often working alone in fields and small workshops, far from public attention. Goddard's work was especially important, though not widely recognized in his time. He tested small rockets that used liquid fuel instead of solid propellants, discovering that controlled combustion could create steady thrust. Many of his experiments failed. Some rockets exploded. Others rose only a few feet before falling back to Earth. But each test taught something new, and slowly, the idea of a rocket stopped being purely theoretical. Still, in the early 1900s, the concept of reaching space remained distant. Society had not yet developed the technological foundation required for sustained flight beyond the atmosphere. Engines were still primitive. Materials were heavy. Computing was non-existent in the modern sense. Even aviation itself was only beginning to take shape. To most people, the moon remained what it had always been, a light in the sky, not a destination. But history rarely moves in straight lines. It builds quietly, layer by layer, often in places that seem disconnected at first. While scientists and inventors were sketching early rocket concepts, the world itself was changing in ways that would unintentionally accelerate everything. Industrialization was advancing rapidly. Electricity was transforming cities. Communication was becoming faster. And with each decade, machines became more capable of supporting ideas that once seemed impossible. Still, rockets remained fragile curiosities. There was no clear purpose for them yet beyond experimentation. No global race. No national program. Just scattered individuals, working in isolation, slowly discovering that the universe did not forbid space travel. It only made it difficult. And then, gradually, the tone of the world began to shift. By the early 20th century, technology and conflict became increasingly intertwined. Engineering advancements were no longer purely academic. They were becoming strategic. The same precision required to design experimental rockets would soon be applied in entirely different contexts, driven by forces far larger than any single scientist. It is often in this kind of environment, unsteady, competitive, uncertain, that breakthroughs begin to accelerate. What had once been slow, individual curiosity started to converge into organized development. Governments began to take interest in propulsion systems. Engineers who had once worked alone were now part of larger projects. Ideas that had once been speculative were being tested with greater resources and urgency. And beneath all of this, something important was forming without being fully recognized yet. a shift in perspective. The idea that the sky was no longer a boundary, that it might be a beginning. Still, no one had gone to space. No one had left Earth. The moon remained untouched, unchanged, indifferent to all human progress below it. But the foundation was being laid. Quietly, patiently, one calculation at a time, one experiment at a time. And in the distance, beyond failures, beyond early prototypes, beyond the slow accumulation of knowledge, there was the faint outline of something new taking shape. Not yet a program, not yet a mission, but a possibility. And that possibility would soon be pushed forward by forces far larger than any individual imagination could contain. The world was approaching an era where rockets would no longer be just experiments. They would become instruments of history, and the age of true spaceflight was beginning to come into view. For a brief moment in history, rockets were still just ideas being tested in quiet laboratories. Small experiments, fragile engines, careful calculations written on paper and rewritten again after failure. But history rarely allows ideas to stay quiet for long. As the world moved deeper into the 20th century, the balance between science and conflict began to shift. The same technologies that had been developed out of curiosity or academic interest started to take on new meanings. Speed, distance, and precision were no longer just engineering challenges. They were becoming matters of strategy. And in that shift, rocket development changed forever. During the Second World War, rocketry advanced rapidly, not because humanity had suddenly solved the technical challenges, but because necessity demanded progress at any cost. Among the most significant developments of this era was the V-2 rocket, created in Germany under the direction of Wernher von Braun. It was not the first rocket ever built, but it was one of the first to demonstrate controlled, long-range flight powered by liquid fuel and guided systems. It rose higher and faster than anything before it, briefly touching the edge of what could be considered space before descending back toward Earth at devastating speed. To many, it was a weapon, but to engineers, it was also something else. A proof that rockets could be made powerful enough to leave the ground in a controlled and repeatable way. After the war ended, the world was left with both devastation and an unexpected inheritance. Technology that had been developed for destruction, but that also contained the blueprint for exploration. Scientists and engineers who had worked on wartime rocket programs were relocated, recruited, or reassigned. Their knowledge did not disappear. Instead, it moved, across borders, across institutions, across governments that now understood that rocket technology had implications far beyond warfare. In the United States, captured German engineers and designs were studied and integrated into emerging aerospace programs. Wernher von Braun himself would eventually become a central figure in American rocket development, helping to guide early missile systems and later, space exploration vehicles. It is one of history's quiet contradictions. The same minds that built weapons of war would later help design machines intended to leave Earth entirely. But at this stage, the focus was still grounded. Cold War tensions were rising between global powers, and rockets were seen first and foremost as strategic tools. Long-range missiles became a priority. The ability to project force across continents changed military planning entirely. Funding and research increased rapidly, but the goal was not the moon. Not yet. Still, even in this period of competition and fear, something important was happening beneath the surface. Every advancement in propulsion, every improvement in guidance systems, every successful test flight, even those designed for military purposes, was also building the foundation for something larger. Because once a rocket becomes reliable enough to reach high altitude, it is only a matter of scaling before it can leave Earth completely. And that idea began to take hold quietly within scientific communities. Not as a political goal, but as a technical possibility. By the late 1950s, the world had entered a new phase of technological awareness. Radio communications had advanced. Computers, though still large and limited, were beginning to assist in calculations that would have taken humans far longer to complete. Materials science had improved. Jet propulsion had become more refined. And rockets were no longer experimental curiosities. They were becoming systems. Then, in 1957, everything shifted again. A small object was placed into orbit around Earth, Sputnik 1. It was not large. It was not complex. It did not carry passengers or instruments of great scientific depth by modern standards. But it did something unprecedented. It confirmed that human-made objects could remain in space. And with that confirmation, the abstract idea of space travel became suddenly real. A machine built on Earth had entered orbit and continued circling above it, silent and consistent, passing over continents and oceans every 96 minutes. For many people, it was awe. For others, it was alarm. Because if one nation could place something in orbit, another could follow. And if satellites were possible, then so too were far more advanced systems, communication networks, observation platforms, and eventually, vehicles capable of reaching even farther. The launch of Sputnik marked the beginning of what would soon be called the space race, a competition not just of technology, but of national ambition, scientific capability, and political identity. The response was immediate. Programs were reorganized. Funding increased. New agencies were formed. In the United States, NASA would soon be established to unify and accelerate space efforts. And suddenly, what had once been a distant academic dream became a national priority. Still, even as urgency grew, the path forward was not yet clear. No one had sent a human into orbit. No one had landed on the moon. The necessary technology still had to be tested, refined, and proven step by step. But the direction of history had already changed. The rockets were no longer just weapons. They were no longer just experiments. They were becoming bridges. Bridges between Earth and the space beyond it. And somewhere ahead, at the far end of that bridge, waiting in silence, was the moon. For most of human history, the sky had been a ceiling, invisible, unquestioned, and absolute. But by the middle of the 20th century, that ceiling had begun to crack, not physically, but conceptually. Humanity was slowly discovering that the atmosphere was not a boundary in the way it had once seemed. It was something that could be passed through, something that could be left behind. And once that realization took hold, everything changed. The first clear sign came quietly. On October 4, 1957, a small metallic sphere was launched into orbit around the Earth. It was called Sputnik 1. It did not carry people. It did not carry instruments of great complexity. It did not transmit detailed scientific data in the way modern spacecraft do. By later standards, it was simple. But its simplicity was not what mattered. What mattered was what it proved. A human-made object had entered orbit and remained there. Circling the planet in a steady rhythm, it moved through the sky like a silent signal that something fundamental had shifted. Every 96 minutes, it completed a journey around the Earth, passing over continents, oceans, cities, and deserts, indifferent to borders, weather, or time. And it kept going. For those who heard its radio signal, it was a faint, repetitive pulse, a steady beep that could be tracked from the ground, something artificial, yet unmistakably real, moving overhead where nothing human had ever stayed before. The reaction on Earth was immediate. For many, it was awe. For others, it was uncertainty. because Sputnik did not exist in isolation. It represented capability, and capability, once demonstrated, naturally raises questions about what else might be possible. If one nation could place an object in orbit, then another could follow. And if satellites could be built, then larger systems might not be far behind. The space age had begun, not with celebration, but with awareness, a recognition that a new domain of human activity had opened, one that no civilization had ever truly entered before. Governments responded quickly. Research programs were expanded. Funding increased. Scientific institutions were reorganized to prioritize space-related development. The United States, in particular, moved to coordinate its efforts under a unified agency. In 1958, NASA, the National Aeronautics and Space Administration, was established. Its purpose was simple in wording, but immense in scope: to explore space, to develop flight beyond Earth, and to coordinate the technologies required to do so. But even with new institutions forming, the path forward was not yet clear. Orbit had been achieved. But orbit was only the beginning. The real challenge was far greater: understanding how to send humans into space safely, how to bring them back, and how to survive the harsh conditions beyond Earth's atmosphere. Rockets still failed frequently. Guidance systems were still developing. Heat shields, life support systems, and re-entry techniques were all in early stages of design. Each success was fragile. Each failure provided data, but also delay. And yet, progress continued, because the direction of history had already been set. In 1958 and 1959, the United States launched a series of early satellites and test missions. Some succeeded, others failed. Each one revealed something new about the environment above Earth. Radiation levels, atmospheric drag, communication delays. Orbital mechanics that had previously been theoretical became measurable reality. Meanwhile, the Soviet Union continued its own rapid progress, escalating the sense of competition between the two global powers. This period became known as the space race, not a formal war, but a sustained competition defined by achievement and symbolism. Every launch carried meaning beyond its technical purpose. Every success was interpreted globally, not just scientifically, but politically. Still, beneath the tension, something remarkable was happening. Humanity was learning how to leave Earth. Step by step, systems were being refined. Rockets were becoming more reliable. Tracking systems more precise. Engineering knowledge was expanding faster than at almost any previous point in history. And even though no human had yet reached orbit, the idea was no longer abstract. It was approaching reality. The sky, once a fixed boundary, was becoming a navigable space, a region that could be measured, calculated, and eventually traveled through with intention. The moon, still distant and silent, remained unchanged during all of this. It did not respond to Sputnik. It did not acknowledge NASA. It did not shift or react as human technology advanced. But for the first time in history, it was no longer out of reach in imagination. It was becoming a destination in planning documents, in engineering diagrams, in quiet discussions between scientists who understood that orbit was not the end of the journey. It was the beginning. And as the 1950s came to a close, one truth was becoming increasingly clear, even if it had not yet been publicly stated in full. If a machine could orbit the Earth, then a human could follow. And if a human could orbit the Earth, then the moon was no longer impossible. It was only far. And distance, as history was beginning to show, was something that technology could slowly erase. The next step would not be small, but it would be inevitable. At first, Space had been something measured only by machines. Rockets, satellites, signals bouncing silently around the Earth. These were the first messengers of a new era. But for all their importance, they were still extensions of human intention, not human presence. The next step would change that entirely. Because once machines had proven that orbit was possible, the question shifted in a quiet but profound way. If a machine can go, then what about a person? It was no longer just about engineering capability. It became about survival, about whether the human body itself could endure what lay beyond the atmosphere. The acceleration, the vacuum, the radiation, the silence. Everything had to be tested not just for performance, but for life. And so began a new phase of the space age, one defined not by objects circling the Earth, but by humans crossing into it. The Soviet Union moved first. On April 12, 1961, a spacecraft named Vostok 1 carried a single human into orbit. His name was Yuri Gagarin. He did not travel far in the way distance is usually measured on Earth. In fact, he remained relatively close to the planet's surface compared to astronomical scales. But what mattered was not distance. It was separation. For the first time in history, a human being was no longer on Earth. He was above it, orbiting it, moving through space at incredible speed, completing a full circuit of the planet in just under 2 hours. Inside the spacecraft, everything was controlled and confined. Instruments surrounded him. Systems monitored every condition. The environment was carefully engineered to sustain life in a place where life was not supposed to exist. And yet, from his perspective, the Earth below was quiet and continuous. Clouds drifting over continents. Oceans reflecting sunlight. A planet turning slowly beneath him, indifferent to the small capsule passing overhead. When Gagarin spoke during the mission, his voice carried a calmness that contrasted with the enormity of what was happening. He described the view, the experience, the sensation of weightlessness. Simple words for something that had never been experienced before. And then, after a single orbit, he returned. The spacecraft re-entered the atmosphere, endured intense heat, and descended back toward Earth. Humanity had crossed a threshold. But the implications of that moment were far larger than the flight itself. Because if one person could survive orbit, then others could follow. And if orbit was possible, then longer missions, more complex spacecraft, and eventually lunar travel were no longer abstract ideas. They were engineering problems waiting to be solved. The world reacted immediately, some with celebration, some with concern, some with disbelief that such a thing had happened so quickly. The psychological impact of a human in space was far greater than that of any satellite. It made the concept real in a way machines alone never could. Not long after, the United States responded with its own human spaceflight program. Alan Shepard became the first American in space in 1961, though his flight was suborbital, brief, arcing upward before returning to Earth. It demonstrated control, precision, and growing confidence in spacecraft systems. But orbit was still the true milestone. And that milestone would come in 1962 with John Glenn, who became the first American to orbit the Earth. His mission aboard Friendship 7 marked a turning point for NASA. It proved that the United States could not only launch humans into space, but sustain them in orbit and bring them back safely. Each of these missions added a layer of understanding, not just about rockets or technology, but about the human body itself, how it reacted to weightlessness, how it adapted to isolation, how it functioned under conditions that had never existed in human experience before. And beneath the technical achievements, something else was happening. Confidence was growing. Not confidence in the sense of certainty, but in the sense of momentum. Each successful flight made the next one possible. Each risk taken expanded the boundary of what was considered achievable. And as this momentum built, political pressure also increased. Because space was no longer just exploration. It was demonstration, a visible measure of technological progress between nations, watched closely by the entire world. Every mission carried meaning beyond its scientific goals. Every success suggested capability. Every delay suggested limitation. And so the pace accelerated. More tests. More launches. More preparation. Behind the scenes, engineers and scientists were already looking ahead. Beyond Earth orbit. Beyond short missions. Beyond even the idea of staying in space for days or weeks. Their attention was slowly turning toward a more distant target. A world that had always been there in the night sky. The moon. Still untouched. Still silent. Still far beyond anything a human had ever attempted. But no longer unthinkable. Because now, for the first time, humanity had proven something essential. A person could leave Earth. And return. And once that had been established, the next question became unavoidable. How far could they go before they stopped coming back? For a brief moment, the space race had been defined by achievement. First satellites. First human in orbit. First American flights into space. Each milestone had been significant on its own, but together they formed something larger, a pattern that was becoming impossible to ignore. Step by step, humanity was moving outward, away from Earth, into a domain that had once belonged only to observation and imagination. But by the early 1960s, the question was no longer whether humans could reach space. It was how far they could go, and more importantly, who would set the next defining goal. At this point, the United States and the Soviet Union were moving in parallel directions, each pushing their own programs forward with increasing intensity. Success in space had become deeply connected to national identity, scientific prestige, and global influence. Every launch carried weight far beyond its engineering purpose. Every success was seen as progress. Every delay, a setback. And yet, despite all the momentum, there was still no clear destination beyond Earth orbit that had been publicly defined as the next major objective. That changed in 1961. In a moment that would become one of the most important declarations in space history, President John F. Kennedy addressed a joint session of the United States Congress. The message was not tentative. It was not gradual. It was direct. The United States, he said, should commit itself to landing a man on the moon and returning him safely to Earth before the decade was out. At the time, this was not a plan. It was not a technical roadmap. It was a national commitment to a goal that had not yet been fully engineered. The moon, still distant and silent, had now been named as a destination. And just like that, the entire direction of American space efforts shifted. NASA, still in its early years, was suddenly tasked with achieving something unprecedented in human history. Not just reaching space, not just orbiting Earth, but traveling nearly 250,000 miles away, landing on another celestial body, and returning safely. It was a goal that required a level of coordination and technological development that did not yet exist. But it also provided something essential: focus. For the first time, the scattered efforts of rocket development, orbital testing, and human spaceflight were being pulled into a single, unified objective. Everything would now be built toward the moon. Inside NASA, the implications were immediately understood. This would require new rockets far more powerful than anything yet built. It would require spacecraft capable of deep space navigation, life support systems for extended missions, and entirely new methods of landing on a surface no one had ever touched. It would require solving problems that had not even been fully defined yet. And it would require doing all of this within less than a decade. The scale of the challenge was difficult to comprehend. But the commitment had been made. In engineering terms, Apollo began to take shape not as a single project, but as an entire ecosystem of technologies. The Saturn rocket family was conceived as the launch vehicle powerful enough to break Earth's gravitational hold with a full lunar mission payload. The spacecraft itself would need to be divided into modules, each with its own function, each solving a specific part of the journey. One for reaching space, one for traveling through it, one for descending to the lunar surface, and one for returning home. Every piece had to work not only individually, but together, flawlessly, in an environment where repair would not be possible. At the same time, astronauts were being selected and trained not just as pilots, but as test subjects in an entirely new kind of environment. Simulators were built to replicate lunar conditions as closely as possible. Underwater training was used to mimic reduced gravity. Navigation systems were practiced repeatedly until precision became instinct. And yet, despite all this preparation, there was still a fundamental uncertainty. No one had ever tried this before. Everything was being built on theory, testing, and incremental confidence. And as the program expanded, so too did its visibility. The Apollo program became more than an engineering project. It became a symbol, a demonstration of what could be achieved when science, government, and industry aligned toward a single goal. But symbols carry pressure, and pressure, in spaceflight, is never abstract. It is measured in tolerances, in fuel margins, in structural integrity, in seconds of error that can mean success or failure. Behind the public optimism, engineers were constantly aware of how narrow the margins truly were. Every system had redundancy, but also limits. Every solution introduced new complexity. Every success in testing revealed new challenges in scaling. And still, the work continued, because there was no alternative path that led to the moon. By the mid-1960s, Apollo had become one of the most ambitious undertakings in human history. It was no longer just about proving capability. It was about executing a plan that had never been executed before, under conditions that could not be fully simulated on Earth. And yet, something important had shifted in human thinking. The moon was no longer a distant object of mythology or quiet observation. It was a target, a place that could be approached methodically, measured, studied, reached, and returned from. Kennedy's declaration had not just set a goal. It had created a timeline, a direction that every subsequent mission would follow. "We choose to go to the moon," he had said, "not because it was easy, but because it was difficult." And in that difficulty, the entire space program found its purpose. From this point forward, every test, every launch, every failure, and every success would be part of a single unfolding path, a path that led away from Earth, and toward a place that, until now, had never been touched by human hands. Once the goal had been set, and the direction made clear, the real work began. The moon was no longer an idea drifting in the background of human imagination. It had become a deadline, a target, a physical place that would require machines capable of reaching it, landing on it, and returning safely. And unlike everything that had come before, there was no existing blueprint for how to do that. Apollo was not a single invention. It was a system, an entire architecture of technology, designed from the ground up to solve a problem that had never been solved before. Every part of it had to be created specifically for lunar travel. Every failure would cost time. Every success would redefine what was possible. At the center of this effort stood one of the most powerful machines ever built, the Saturn V rocket. Towering over 360 feet tall, the Saturn V was not just large. It was engineered to escape Earth's gravity with enough energy to send multiple tons of equipment, supplies, and human life toward another world. Its power came from stages, each designed to do a specific part of the journey. The first stage provided the enormous thrust needed to lift the entire structure off the ground. Its engines burned through fuel at a rate that was almost difficult to comprehend, pushing against Earth with a force strong enough to make the rocket rise slowly, deliberately, almost like it was unwilling to leave. Once its job was complete, it detached, falling away, discarded. The second stage continued the acceleration, pushing the spacecraft higher, faster, thinner into the atmosphere. And then it too separated. The third stage would complete the push into orbit and prepare the trajectory toward the Moon. Each stage was essential. Each stage existed only briefly, and each one had to work perfectly. There was no margin for partial success. While the rocket provided the power, the spacecraft itself carried the complexity. The Apollo spacecraft was divided into distinct modules, each designed for a specific phase of the mission. The command module housed the astronauts during launch, travel, and return. It was the only part that would survive re-entry into Earth's atmosphere. Everything else would be left behind. Attached to it was the service module, which provided propulsion, power, oxygen, and essential systems during the journey. And then there was the lunar module, perhaps the most unusual spacecraft ever designed. It was not built for Earth. It was not aerodynamic. It could not fly in atmosphere. It was designed only for space and for landing on a surface with no air, no weather, and no familiar reference points. It would descend to the Moon and later lift off from it again, leaving its lower stage behind on the lunar surface. Every component of Apollo reflected this philosophy. Nothing extra, nothing unnecessary, only what was required to complete the mission. But building the hardware was only part of the challenge. There were also the people. Astronauts were selected not just for their experience, but for their ability to remain calm in environments that were inherently unstable. Many were test pilots, individuals already accustomed to high-risk flight and rapid decision-making. But even for them, Apollo was different. No test flight could fully replicate the conditions of leaving Earth entirely. No simulation could perfectly recreate the silence of deep space or the isolation of lunar distance. Training became a constant cycle of repetition and refinement. Simulators recreated cockpit environments down to the smallest detail. Astronauts practiced navigation, docking, and emergency procedures until responses became instinctive. Underwater training helped simulate reduced gravity, allowing movement practice in an environment that partially mirrored the Moon's surface. And always, there was the awareness that mistakes in space were not easily corrected. Every decision had to account for distance, time delay, fuel limits, system constraints. Even communication with Earth would not be instantaneous in a practical sense. Everything required preparation before launch, because once the mission began, Earth would become distant in both physical and operational terms. Meanwhile, engineers on the ground worked continuously to refine the systems that would make all of this possible. Propulsion systems were tested repeatedly, sometimes failing in dramatic ways that required redesign. Guidance computers were developed to perform calculations that had previously required entire rooms of equipment. Materials had to withstand extreme temperature shifts, from the intense heat of launch to the cold vacuum of space to the fiery return through Earth's atmosphere. Each problem solved revealed new layers of complexity. And yet, progress continued. Because Apollo was not just a project anymore. It was an infrastructure of collaboration across thousands of people, engineers, scientists, technicians, contractors, each contributing to a system so large that no single person could fully comprehend it in its entirety. It was built piece by piece, decision by decision, test by test, and slowly it began to take shape. By the mid-1960s, hardware was being assembled. Components were being tested together. Early missions began to move from theory into reality. But beneath all of this technical progress was something quieter, almost invisible, a growing awareness that the moon was no longer abstract. It was approaching, not quickly in human terms, but steadily in engineering terms. Every completed test brought it closer. Every successful launch reduced uncertainty. Every solved problem removed one more barrier between Earth and another world. And in that gradual reduction of uncertainty, something remarkable was happening. The impossible was becoming structured, defined, executable. Apollo was no longer a question of whether it could be done. It was becoming a question of how carefully it had to be done in order to succeed. And somewhere ahead, beyond the complexity of systems and stages and simulations, the moon waited, silent, unchanged, and entirely unaware of the machinery being built to reach it. By the mid-1960s, Apollo had become more than a program. It was a national effort, a technological commitment, a vast, interconnected system of engineering, testing, manufacturing, and training operating under immense pressure and even greater expectations. Everything was moving forward. But space exploration has never progressed in a straight, uninterrupted line. Every advance carries risk. And in 1967, that risk revealed itself in the most devastating way yet. Apollo 1 was not a mission to the moon. It was a ground test, a simulation designed to verify systems inside the command module before flight. The spacecraft was sealed. The astronauts were inside. Procedures were being tested under conditions meant to approximate the early stages of launch. But even on the ground, even without leaving Earth, spaceflight hardware remained unforgiving. Inside the command module were 3 astronauts, Gus Grissom, Ed White, and Roger B. Chaffee. They were experienced, trained, and deeply familiar with the risks of their profession. Test pilots by background, they understood that progress in aerospace had always come with danger. Every generation of flight had been defined by those willing to push systems beyond what had been safely proven. But what happened that day was not part of a planned test outcome. During the simulation, a fire ignited inside the cabin. The exact cause was a combination of factors: oxygen-rich atmosphere, flammable materials, and a sealed environment that made escape impossible once the fire began. In moments, conditions inside the capsule became unsurvivable. The hatch, designed to open inward and secured by internal pressure, could not be opened quickly enough under emergency conditions. Within seconds, communication was lost, and with it, 3 lives. The shock that followed extended far beyond NASA. For the space program, Apollo 1 became a defining moment, not of progress, but of consequence. For the first time in the race to the moon, the reality of what was being attempted became impossible to ignore in its full weight. This was not just engineering. It was human life operating at the edge of known capability. Everything stopped. Not permanently, but decisively. The Apollo program was grounded. Investigations began immediately. Every aspect of the spacecraft was examined in detail. Materials, wiring, procedures, design choices, safety protocols. Nothing was considered too small to review. What emerged from this process was not a single cause, but a system of vulnerabilities. design decisions that had been made under pressure to meet deadlines, material choices that were acceptable in theory but dangerous in practice, procedural assumptions that had not fully accounted for emergency conditions inside a sealed environment, and perhaps most importantly, a culture that had prioritized speed toward a goal that now seemed even more distant in the aftermath. The fire forced a complete re-evaluation of Apollo's design philosophy. The spacecraft had to change. Safety standards had to change. Even communication practices and testing procedures had to be restructured from the ground up. 4 months, progress slowed. But what replaced it was something essential: correction. Engineering is often thought of as building forward. But in reality, it also requires stepping back, identifying failure not as an endpoint, but as information. Apollo 1 became a reference point for everything that followed, a permanent reminder of what happens when complexity outpaces caution. The redesign of the command module introduced new materials that were less flammable. The hatch was re-engineered to open outward and rapidly in emergency conditions. Electrical systems were rerouted and insulated more carefully. Safety protocols became stricter, more detailed, and more realistic in their assumptions about what could go wrong. It was a difficult period for NASA. Public confidence wavered. Internal morale was strained. The goal of reaching the moon had not changed, but the path forward had become more complex, more cautious, and more aware of its own fragility. And yet, despite the setback, the direction of the program did not reverse. Because Apollo was no longer just a response to competition or political ambition. It had become something deeper, a structured attempt to do something unprecedented, with full awareness of the cost of failure. In time, the program resumed. Carefully, methodically, with redesigned spacecraft and revised procedures. Testing began again. Unmanned missions were prioritized to validate systems. Each component was reintroduced under stricter scrutiny than before. Progress returned, but it returned differently. Slower, more deliberate, more aware. And in that shift, something important changed within the program itself. Apollo was no longer driven only by momentum toward the moon. It was now also guided by restraint, by the understanding that reaching another world required not only ambition, but precision that could withstand the consequences of error. The moon had not moved closer during this time. It had remained where it always was, silent, distant, unchanged. But humanity's path toward it had changed irrevocably. It was no longer a straight ascent. It was a careful ascent, one built not only from innovation and courage, but from lessons learned at the highest possible cost. After the tragedy of Apollo 1, the space program did not rush forward. It recalibrated. What had once been a race driven by urgency became something more deliberate. Every system, every procedure, every assumption was now examined under a new level of scrutiny. The goal had not changed, but the path toward it had become far more careful. Before humans could attempt the moon again, the machine itself had to be proven. Piece by piece, step by step. Apollo was no longer just a concept in engineering documents. It was a system that needed to demonstrate reliability in the most unforgiving environment humans had ever attempted to enter. And so the missions resumed, but differently. Not with a lunar landing. Not even with astronauts leaving Earth orbit at first. Instead, NASA began a sequence of increasingly complex tests designed to validate each stage of the system independently. Apollo 7 marked the return of human spaceflight for the program. It stayed in Earth orbit, testing the redesigned command module. Every system was monitored in real time. Communications, propulsion, navigation, life support, all evaluated under actual flight conditions. It was not dramatic in the way public imagination often expects spaceflight to be. It was methodical, almost routine. But behind that routine was something critical: trust being rebuilt. Once Apollo 7 confirmed the command module could safely support a crew in orbit, the program moved forward again. This time, beyond Earth itself. Apollo 8 became one of the most significant early steps in the entire program. It was the first mission to leave Earth orbit entirely and travel to another world. For the first time in history, humans would leave the gravitational influence of their home planet and journey toward the Moon. The decision to send Apollo 8 to lunar orbit was not simple. It was a bold adjustment to the program schedule, driven in part by competition and in part by confidence in the redesigned systems. But it also carried risk, because no human-rated spacecraft had ever traveled that far before. As Apollo 8 accelerated away from Earth, the familiar view of home began to shrink. The blue and white sphere that had always dominated human perspective slowly became smaller, quieter, more distant. And then, for the first time, the astronauts saw something no human had ever seen with their own eyes: the far side of the Moon, a surface perpetually hidden from Earth, now visible in stark detail as the spacecraft entered lunar orbit. Gray, cratered, silent, a landscape untouched by human history. Inside the spacecraft, systems continued their steady operation. The crew monitored trajectory, adjusted navigation, and maintained constant communication with mission control. Every orbit around the Moon was both a technical accomplishment and a psychological shift, a reminder that humanity had extended its presence beyond Earth for the first time. And then came a moment that would become one of the most iconic images in human history. As Apollo 8 rounded the Moon, Earth appeared above the lunar horizon, a small, fragile sphere rising over a barren landscape, blue, white, and suspended in darkness. The image became known as Earthrise. It was not just a photograph. It was a shift in perspective. For the first time, humanity saw its home not as an infinite backdrop, but as a single, finite world floating in space. Small, isolated, alive. The effect was profound, even for those trained to remain focused on procedure. The mission was still operational, still technical, still governed by checklists and orbital mechanics, but it was also something larger, a reminder of what was being risked, and what was being reached for. Apollo 8 returned safely to Earth, proving that a spacecraft could travel to the Moon, enter orbit, and return without landing. It validated key systems that would be required for the next step: descent. The Moon was no longer just a distant object of observation. It was a destination that had been approached, circled, and studied from close range. And now, the only remaining challenge was the most complex of all: landing. The next Apollo missions continued this progression. Apollo 9 tested the lunar module in Earth orbit, separating and rejoining components to simulate lunar operations. Apollo 10 brought the lunar module into lunar orbit itself, descending close to the surface without actually landing, essentially rehearsing the final approach. Each mission reduced uncertainty. Each test brought the system closer to readiness. The lunar module, once an abstract engineering solution, now existed as a fully functional vehicle capable of operating in lunar conditions. Guidance systems had been refined. Landing procedures had been simulated repeatedly. Fuel margins, descent angles, and surface conditions had all been studied in increasing detail. And yet, despite all the preparation, one essential step remained untested: touching down on the surface itself. The Moon was now close enough to be reached, but still far enough that nothing could be taken for granted. Everything had been tested, except the final moment. The descent. The landing. The silence of contact with another world. And beyond that moment, what it would mean to stand on a place that no human had ever stood before. The next mission would attempt exactly that. Apollo 11. And nothing in the history of exploration had yet reached that point. By the time Apollo had reached the stage of lunar rehearsals, the hardware was no longer the only focus. The machines were becoming ready. The procedures were becoming refined. The path to the moon was narrowing into a sequence of steps that had been tested, repeated, and slowly understood. But there was still one essential question remaining. Who would go? Not every astronaut in the program would have the chance to walk on the moon. The Apollo missions required a rotation of crews, backup teams, support teams, prime crews. Years of training, simulation, and preparation all led toward a small number of actual flight opportunities. And at the center of that structure, one mission stood above all others. Apollo 11. The first attempt to land a human being on another world. Selecting the crew for this mission was not a simple matter of ranking experience. It was a careful balance of skill, judgment, and temperament. Every astronaut in consideration had already proven themselves in flight training, engineering understanding, and high-pressure decision-making. But the moon mission required something more. It required stability under absolute uncertainty. The crew that was ultimately chosen reflected that balance. Neil Armstrong, Buzz Aldrin, Michael Collins. Each brought a different kind of expertise to the mission, and together they formed a team capable of handling the immense complexity of lunar travel. Neil Armstrong was selected as commander. Known for his calm demeanor and precise thinking, he had a background as a test pilot and engineer. His ability to remain steady in rapidly changing conditions was one of the defining reasons for his selection. In an environment where decisions would have to be made in seconds, that steadiness mattered more than anything else. Buzz Aldrin, a pilot and engineer with a strong academic background in orbital mechanics, brought a deep understanding of rendezvous and docking procedures. His doctoral work had focused on orbital flight techniques, knowledge that would become essential during lunar operations, where spacecraft would have to separate, descend, and reconnect in space. Michael Collins, serving as command module pilot, had the responsibility of remaining in lunar orbit while the other two descended to the surface. His role was often described as the most isolated position in the mission. While Armstrong and Aldrin would be on the moon, Collins would remain alone in orbit, responsible for navigation, systems monitoring, and the critical task of rendezvous once the lunar module returned. Together, the three roles formed a complete system. One for descent, one for surface operations, one for return and coordination. But beyond technical roles, there was something equally important: compatibility. Spaceflight places humans in conditions that are inherently isolating. Confined spaces, limited communication, and the constant awareness that every system must function correctly create an environment unlike anything on Earth. In such conditions, interpersonal stability becomes just as important as technical skill. NASA understood this deeply. The selection process considered not just individual ability, but how each astronaut functioned within a team over extended periods of training and simulation. And so, Apollo 11 was not just assembled, it was balanced. Once the crew was assigned, preparation intensified. Training was no longer general. It became mission-specific. Simulators replicated the exact configuration of the spacecraft they would fly. Every switch, every panel, every sequence of procedures was practiced repeatedly until it became second nature. Emergency scenarios were introduced without warning. Systems were deliberately failed in simulations to test response under pressure. The goal was not perfection in ideal conditions. It was reliability under stress. At the same time, mission control teams were preparing alongside them. Apollo was not just a spacecraft and a crew. It was an entire network of people on the ground responsible for guidance, communication, and decision support. Every trajectory calculation, every correction burn, every procedural update was coordinated between the spacecraft and Earth in real time. And yet, even with all this preparation, there was an underlying awareness that could not be eliminated. Apollo 11 would be different. Unlike earlier missions, this one would not stop short of the Moon's surface. It would not orbit and return. It would not test and observe from a distance. It would attempt the final step. Landing, touching another world, and returning safely. The margin for error was small. Fuel calculations were precise but unforgiving. The lunar surface was not fully known in detail. Landing sites had been studied from orbiting spacecraft, but no human had ever seen them up close. There was uncertainty in terrain, in lighting, in dust behavior during descent. And there was the simple reality that no simulation could fully replicate what it meant to descend toward a surface that had never been physically touched by human life. Still, the mission moved forward. Because by this point, Apollo was no longer experimental in the traditional sense. It was operational. Every mission before it had built confidence. Every test had removed another layer of uncertainty. Apollo 11 stood on the accumulation of all those earlier steps. Apollo 7 had proven the spacecraft could support humans. Apollo 8 had proven it could travel to the Moon. Apollo 9 had proven the lunar module could function in space. Apollo 10 had rehearsed the descent without landing. Now only one step remained untested, and the crew assigned to take that step understood its significance fully. They were not just preparing for a mission. They were preparing for a moment that would be observed by the entire world, for a point in history that would be measured not only in engineering success, but in human experience. And as the final preparations continued, one truth became increasingly clear. Everything built up to this point, every rocket, every test, every redesign, every correction, had been leading to a single sequence of events. A descent toward a silent surface. A landing that had never been attempted before. And a moment that, once reached, would change the way humanity understood its place in the universe. In the early hours of July 16, 1969, the world was still quiet. At Cape Kennedy, Florida, the air was heavy with humidity, the kind that settles in before sunrise. The launch complex stood illuminated against the darkness, a towering structure of steel and intention. At its center rested the Saturn V rocket, Apollo 11's launch vehicle, silent for now, but fully prepared for what it had been built to do. Inside it, 3 astronauts were already seated: Neil Armstrong, Buzz Aldrin, Michael Collins. The countdown had been underway for hours, carefully managed, step by step, each system checked and rechecked. Fuel was loaded in stages, cryogenic propellants filling the rocket's massive tanks. Electrical systems were stabilized. Guidance computers were aligned. Communication links were tested and confirmed. Everything that could be controlled had been brought into readiness. But even in this controlled environment, there was a sense of stillness that no simulation had ever fully captured. Because this was no longer preparation. It was beginning. As the final minutes approached, the Launch Control Center entered a rhythm of precision. Each call-out marked another completed checkpoint in a sequence that had been rehearsed countless times. Systems green. Fuel stable. Weather within limits. Trajectory confirmed. And yet, beyond the technical language, there was something else present in the room. a quiet awareness that all of this complexity was converging on a single irreversible moment, when the rocket would leave the Earth. Inside the command module, the astronauts sat in near silence. Their suits were pressurized. Their instruments surrounded them. The capsule was small compared to the immense structure beneath it, but it contained everything necessary to carry human life beyond the planet. There was no dramatic speech inside the spacecraft. No final words. Only focus. Only procedure. T-minus minutes continued to tick down. The engines beneath them were not yet ignited, but the system was already alive with readiness. Thousands of components, each dependent on the others, waiting for the exact instant when ignition would begin. At T-minus 10 seconds, the final sequence began. The Saturn V's F-1 engines ignited in controlled succession. Combustion built rapidly within the engine chambers, transforming chemical energy into raw thrust. Exhaust vents released immense pressure as the rocket prepared to overcome the force holding it to the Earth. And then, lift-off. Slowly at first, almost imperceptibly, the Saturn V rose. The structure that had stood motionless on the pad began to move upward, pushed by a force so powerful that it reshaped the air around it. Flames and exhaust poured downward, striking the launch pad and spreading outward in a violent, controlled storm of energy. The rocket climbed, gradually, deliberately, as if resisting the Earth itself. Inside, the astronauts experienced forces pressing them into their seats as acceleration increased. The rocket was now fully committed to ascent, each stage operating in sequence, each engine contributing to the growing velocity needed to break free from gravity. The sound, felt more than heard, was overwhelming even at a distance. A deep, continuous roar that filled the air around the launch complex and extended outward for miles. And yet, within the spacecraft, procedures continued. Checklists were read. Systems monitored. Trajectory adjustments confirmed. At a specific altitude, the first stage completed its role. Having burned through its fuel, it detached, falling away from the rocket in a controlled separation. The mission continued upward without it, shedding mass to maintain efficiency. The second stage ignited, carrying Apollo 11 higher into the thinning atmosphere. From the ground, the rocket appeared as a bright ascent against the sky, steady, unwavering, moving beyond the familiar boundary of weather and clouds. As it climbed, the sensation of motion changed. The atmosphere grew thinner. Resistance decreased. The Earth below became more distant with each passing second. The transition from surface to space was not a single moment, but a gradual shift, a passage through layers of air until, eventually, there was almost none left. The third stage completed the final push into Earth orbit. For a brief time, Apollo 11 circled the planet. Not yet on its way to the Moon. Not yet beyond Earth's influence. But no longer bound to the surface. Inside the spacecraft, there was a quiet acknowledgement of what had been achieved. All systems were functioning. All stages had performed as expected. The mission was proceeding exactly as designed. But Earth still filled much of their view. Blue and white. Familiar. Still home. The next step would require leaving it entirely. Soon, the rocket would fire again, this time not to stay in orbit, but to escape it. A translunar injection burn that would set Apollo 11 on a trajectory toward the Moon. A path that no human mission had ever taken before. For now, though, there was a brief pause in the journey. A moment between Earth and the Moon. A moment where everything was still working, and everything still felt, for a little while longer, close to home. Once Apollo 11 left Earth orbit, the nature of the mission changed completely. There was no longer any sense of circling home. No familiar horizon. No immediate possibility of return. The spacecraft had entered a trajectory that would carry it outward, away from Earth, toward a destination that no human mission had ever reached before. The trans-lunar injection burn had done its work. The service module's engine fired with precision, increasing velocity just enough to break free from Earth's gravitational hold. It was a carefully calculated push, small in duration, but immense in consequence. After it ended, everything shifted. The Earth began to recede. Not suddenly, not dramatically, but steadily, as distance accumulated second by second. Inside the spacecraft, the crew settled into a new rhythm. Systems checks continued, but the urgency of launch was gone. What remained was a long, quiet phase of travel through space that would last several days. The Moon, still distant, was now the clear destination. Not an idea, not a symbol. A physical place, growing slightly larger in the window as time passed. But between Earth and Moon lay a vast region of emptiness, a silence that could not be experienced on Earth in the same way. No wind, no atmospheric movement, no sound transmission, only the hum of onboard systems and the occasional voice through radio communication. Everything else was still. The astronauts adjusted to this environment in practical ways. Sleep cycles were managed carefully. Equipment was monitored. Navigation readings were taken regularly to ensure the spacecraft remained on course. Small mid-course corrections were performed when needed, brief engine burns that adjusted trajectory with high precision. Even these small adjustments carried significance. In space travel, tiny changes early in a journey could determine whether a spacecraft arrived at its intended destination or missed it entirely. And so every correction mattered. As Earth grew smaller behind them, it began to take on a different appearance. It was no longer a surface of continents and weather systems. From this distance, it became a single object, blue, white, and slowly shrinking into the darkness. A world contained within a fragile sphere. At this stage of the mission, communication with mission control remained steady. Instructions were exchanged, data was transmitted, and systems were monitored continuously. But there was also a growing awareness on both sides that the spacecraft was now largely self-sufficient. The distance meant that responses were no longer immediate in a practical sense of coordination. Planning had to be precise. Procedures had to be pre-verified. Decisions were made with anticipation rather than reaction. Apollo was no longer simply flying. It was moving through a carefully structured path that had been designed years in advance, now unfolding exactly as intended. Inside the spacecraft, routines continued. Food preparation was simple and functional. Equipment was stowed and retrieved as needed. Windows became points of observation during scheduled periods, where the crew could look out at the expanding darkness and the diminishing Earth. And gradually, something subtle began to happen. The sense of scale changed. On Earth, distances feel large in human terms, cities, countries, oceans. But in space, those references dissolve. What remains is only relative position, Earth behind, Moon ahead, and the vastness between them. The Moon itself, at first only a bright disk, began to show structure as they approached. Craters became faintly visible. Shadows hinted at surface irregularities. It was still distant, but no longer abstract. It was becoming real in detail. During the voyage, there were moments of quiet reflection, not in the sense of dramatic realization, but in the slow recognition that the environment outside the spacecraft was unlike anything experienced before. It was not just travel. It was separation. Separation from atmosphere, from sound, from immediate return. Everything aboard the spacecraft existed in a closed system, sustained by carefully engineered life support and mechanical reliability. Outside that system was nothing that could sustain life in the same way. And yet, ahead of them, that same environment contained a destination where human systems would soon attempt to function on another world. As Apollo 11 continued its journey, the moon grew gradually larger, not quickly enough to feel sudden, but steadily enough to mark the passage of time in visible change. Each orbit of the Earth that had once felt significant was now replaced by a continuous forward motion through space. There was no sunrise or sunset in the traditional sense, only shifting light as the spacecraft rotated and moved relative to both Earth and Moon. And then, after hours that blended into days, the Moon began to dominate the forward view. No longer a small object in the distance. No longer just a destination on a chart. It was becoming the primary focus of the journey, a place that would soon capture the spacecraft into its own gravitational influence, a place where everything the program had built toward would finally be tested in full. The voyage was nearing its next transition, from travel between worlds to arrival at one. As Apollo 11 approached the Moon, the spacecraft was no longer simply traveling through space. It was being drawn into it. The Moon's gravity, once distant and subtle, now began to shape the mission in a direct and measurable way. Trajectory calculations that had guided the spacecraft since Earth departure now shifted toward a new objective: lunar orbit insertion. This was the moment where Apollo would stop coasting toward a destination and begin to move around it. To enter lunar orbit required precision. Too much speed, and the spacecraft would pass the Moon and drift back into deep space. Too little, and it could be pulled toward an uncontrolled descent. The timing of the engine burn had to be exact, the direction carefully aligned, the duration calculated down to seconds. There was no room for improvisation. Inside the spacecraft, the crew prepared for the maneuver with quiet focus. Systems were checked again. Trajectory updates were confirmed. The service module engine, the same one used for course corrections, would now perform one of its most critical burns of the entire mission. As the spacecraft reached the far side of the Moon, out of direct communication with Earth, the moment of transition began. There was no voice from mission control. No confirmation from the ground. Only the spacecraft, its instruments, and the Moon filling the view outside the windows. Then the engine ignited. A controlled, sustained burn. Invisible from the outside, but decisive in its effect. The spacecraft's velocity decreased just enough for lunar gravity to capture it. The trajectory that had carried Apollo 11 across hundreds of thousands of miles now bent into a closed path around the Moon. And then, it was in orbit. For the first time in human history, a crewed spacecraft was circling another world. The Moon was no longer something ahead of them. It was beneath them. Outside the windows, the lunar surface stretched into view in a way no telescope on Earth had ever fully conveyed. Craters, ridges, and vast plains of grey dust and rock revealed themselves in shifting light and shadow. The surface was stark, silent, and entirely without atmosphere. There were no clouds, no weather, no sound, only terrain shaped over billions of years. Each orbit brought a new perspective. The spacecraft circled the Moon in steady intervals, passing over regions that had never been seen up close by human eyes. The far side, permanently hidden from Earth, revealed its own rugged landscape, heavily cratered, ancient, and untouched. Inside the spacecraft, systems continued to function normally, but the psychological impact of the view was unavoidable. The Moon was no longer an abstract object in the sky. It was a physical place, detailed and immediate. Close enough to study, close enough to reach. but still distant enough that everything depended on the next phase of the mission. During lunar orbit, final preparations began for the separation of the lunar module. This small, delicate craft, designed specifically for descent and ascent on the Moon, would soon detach from the command module and begin its own journey downward. The crew reviewed procedures repeatedly. Checklists were followed with precision. Communication with Earth resumed as the spacecraft re-emerged from lunar far side, transmitting data and receiving updates. Everything was proceeding as planned. But the weight of what was about to happen was unmistakable. No human had ever attempted to land on the Moon. Orbital flight around it was already historic, but landing would require something entirely different. Controlled descent. Real-time adjustments. Navigation without atmosphere. Landing on terrain that had been mapped only from above. And once that descent began, there would be no simple return to orbit without success. The lunar module would either land, or it would not. As Apollo 11 continued its steady orbit, the separation point approached. The spacecraft was now divided in purpose. The command module, piloted by Michael Collins, would remain in lunar orbit, alone, responsible for navigation and later rendezvous. The lunar module, carrying Neil Armstrong and Buzz Aldrin, would become the descent vehicle. 2 spacecraft, 2 paths, 1 mission. Outside, the Moon continued its silent rotation beneath them, unchanged by the presence above it. But for the crew, everything had narrowed into focus. The next burn would begin the descent, and with it, the most critical phase of the mission would start. A controlled fall toward another world, a landing that had never been attempted, and a silence that, once entered, could not be undone without success. Inside lunar orbit, Apollo 11 had reached its final configuration. The spacecraft that had traveled from Earth was now divided into 2 separate vehicles, each with a distinct purpose, each preparing for a different fate. The command module, piloted by Michael Collins, would remain in orbit around the Moon, alone, circling silently above the surface. The lunar module, carrying Neil Armstrong and Buzz Aldrin, would descend. Its name was Eagle, and before anything else could happen, it had to separate from everything that had brought it this far. The process began with quiet precision. There was no dramatic announcement inside the spacecraft, no sudden shift in atmosphere, only checklists, procedures, and carefully timed commands. Mechanical latches released, connections disengaged, and slowly, almost gently, the lunar module drifted away from the command module. 2 spacecraft that had traveled together across hundreds of thousands of miles were now apart, each following its own path. In that moment, there was no sense of movement as it would be felt on Earth, only relative position changing against the backdrop of the Moon below. Collins remained in orbit, continuing his steady circuit around the Moon, while Armstrong and Aldrin prepared for descent. The lunar module floated free, a fragile structure designed for one purpose only, to take humans down to the surface of another world. Inside, systems came alive in a new configuration. Guidance computers recalculated trajectories. Instruments aligned for descent. Fuel systems pressurized. Every component now focused on a single objective: landing. Below them, the Moon stretched out in silence. Gray terrain. Craters. Ancient surfaces shaped by impacts spanning billions of years. No atmosphere softened the view. Every edge was sharp, every shadow absolute. There was no sound outside the spacecraft. No wind. No movement except orbital mechanics. Then, the descent engine fired. A controlled burn, subtle at first, then sustained. The lunar module began to slow relative to its orbital path. Instead of continuing around the Moon, its trajectory bent downward, toward the surface. This was the beginning of a controlled fall. Not uncontrolled descent. Not free drop. But a carefully calculated reduction in orbital velocity, guiding the spacecraft into a path that would intersect the lunar surface at a precise point. Inside the cabin, Armstrong and Aldrin monitored systems closely. Every reading mattered. Every adjustment had consequences. As the lunar module descended, the Moon grew larger in the windows. The surface that had once been distant and uniform now revealed detail, ridges, boulder fields, and broad plains of fine dust. The landing site in the Sea of Tranquility had been selected for its relative smoothness, but smooth was a relative term. From orbit, it appeared safe. From descent, it revealed complexity. As altitude decreased, the guidance system continued to adjust the descent path. But something unexpected began to emerge. The landing area was not exactly as planned. Large boulders and craters appeared in the projected touchdown zone. The automated guidance was aiming toward a region that could pose risk. At this point in the descent, there was no time for hesitation. Neil Armstrong took manual control. This was not a sudden, dramatic gesture in the sense of action, but a transition of responsibility. The spacecraft still followed its physics, its fuel limits, its programmed constraints, but the final decisions about where to place it on the surface now depended on human judgment. Armstrong guided the lunar module forward, skimming above the surface, searching for a safer landing area. Fuel levels continued to decrease. Time became increasingly finite. The Moon's surface rushed beneath them in slow, silent motion. Crater after crater passed below. Rock fields. Shadows. Uneven terrain that made each moment more critical than the last. Inside Mission Control, thousands of miles away, the situation was followed in real time, but not in real response. Communication delays, data processing, and the nature of spaceflight meant that decisions in the spacecraft had to be made on board. There was only guidance, not control. At a certain point, fuel warnings began to register. The margin for landing was narrowing. Every second mattered, but panic had no place in the process. Procedures continued. Instruments continued to report. And still, the lunar module descended. Lower, closer, searching. Then, a clearer area emerged. A relatively flat surface, free of major obstructions. Not perfect, but usable. Armstrong guided the spacecraft toward it. The descent slowed further. Dust began to rise beneath the engine's thrust, drifting outward in soft, expanding patterns. With no atmosphere, the behavior of the dust was different from anything on Earth. Slow, spreading, illuminated by the sunlight striking the surface. The lunar module hovered just above the ground. Still descending. Still controlled. Still moving toward contact. And then, it touched. Lightly. Quietly. There was no impact sound. No vibration through air. Only confirmation through instruments. The Eagle had landed. For a moment, everything paused. Not in motion, but in significance. The spacecraft sat on the surface of another world. A machine built on Earth, carrying humans, had reached the Moon and come to rest upon it. Inside the cabin, Armstrong and Aldrin remained focused. Systems were still active. Procedures were still ongoing. But the most difficult phase of the descent was complete. The Moon was no longer something below them from orbit. It was outside their landing legs. Solid. Present. Unchanged by their arrival, but now touched by it. And in orbit above, Michael Collins continued to circle, alone, carrying the responsibility of waiting for what would come next. The lunar module sat motionless on the surface of the moon. Its descent had ended, but its systems remained active, humming quietly in a place where sound could not travel beyond the spacecraft itself. Outside, there was only silence, a complete absence of wind, of atmosphere, of anything familiar to Earth. Inside, Armstrong and Aldrin continued working. Every landing was followed by procedure. Every procedure was followed by confirmation. The spacecraft was stable, but stability on the moon meant something different than on Earth. There was no weather to disturb it, no shifting ground in the way oceans or air currents might suggest elsewhere. Only gravity, weak but constant, holding the lunar module gently against the surface. For a moment, the two astronauts remained focused on their instruments. The landing was real, but the mission was not complete. Systems had to be checked. Oxygen levels confirmed. Electrical power verified. Communication with mission control re-established. Then, slowly, the realization settled in. They were not orbiting. They were not traveling. They were on the moon. In mission control, thousands of miles away, the confirmation came through data first. Telemetry signals indicating surface contact, stable systems, and successful shutdown of descent engines. And then came the voice. Houston, Tranquility Base here. The Eagle has landed. A simple sentence. Carefully spoken, but carrying the weight of everything that had led to this moment. For a brief time, there was no response. Not because there was uncertainty, but because the meaning of the words had to be absorbed. After years of preparation, testing, redesign, failure, recovery, and return, the goal had been reached. A spacecraft built on Earth had touched another world. Outside the lunar module, the moon remained unchanged. Its surface had not shifted to accommodate the arrival. Its craters were still shaped by ancient impacts. Its dust remained undisturbed except where the landing engine had briefly stirred it into motion, leaving subtle patterns beneath the craft. No atmosphere carried the sound of arrival. No wind announced the presence of visitors. Only stillness. Inside, procedures continued. But now there was a subtle change in tone. Not urgency, but confirmation. The most difficult phase of the descent was complete, but the mission had entered a new phase entirely. Before any human could step outside, systems had to be stabilized. The lunar module had to be powered down to safe levels while maintaining life support. Environmental conditions had to be monitored carefully. The transition from landing to surface activity required preparation, just as every other phase of Apollo had. And then came the waiting, a pause between arrival and action, a pause that felt different from anything experienced during the journey, because this was no longer travel through space. This was presence, on another world. Outside the small window, the lunar landscape stretched in every direction. Grey terrain, uneven and ancient, shaped over billions of years without air or water to soften its edges. Shadows were sharp, defined by direct sunlight that had traveled uninterrupted across space. The horizon looked closer than expected. The curvature of the moon altered perception in subtle ways, making distances feel both compressed and expanded at the same time. Every detail was unfamiliar, yet real, and soon that surface would be touched directly. Inside the spacecraft, Armstrong and Aldrin began preparing for the next phase, the extravehicular activity. The suits were checked again. Life support systems were verified. Communications were tested. Each step was deliberate, practiced, and repeated in simulation countless times on Earth. But now, simulation was behind them. Everything from this point forward would be real in a way nothing on Earth could fully replicate. The hatch remained closed. For now. Outside, the moon waited in silence. Not anticipating. Not reacting. Simply existing, as it had for billions of years before any human presence reached it. And inside the lunar module, 2 astronauts prepared for the first steps onto that surface. Steps that would follow soon, and would change the scale of human experience forever. Inside the lunar module, the final preparations were complete. Every system had been checked. Every procedure confirmed. Every switch, every valve, every line of communication had been reviewed and re-reviewed until there was nothing left to adjust except timing. Outside the small craft, the moon remained unchanged. A silent landscape that had existed for billions of years without interruption. Now, it waited. Inside, Neil Armstrong and Buzz Aldrin prepared for the moment that would define the next step in human exploration. The cabin was small, functional, and tightly organized. There was no excess space, no unnecessary movement. Everything had been designed for efficiency in an environment where every gram, every watt, every second mattered. Armstrong began the process of opening the hatch. It was not immediate. It was not simple. Each step required care, because even in a vacuum, mechanical systems behave with their own constraints and limitations. The interior of the lunar module had been maintained carefully throughout descent and landing, and now it had to transition into a new configuration. Slowly, carefully, the hatch was opened. Beyond it was not air, not sound, not atmosphere, only the moon. A view that had never been seen directly by human eyes from this position before. The surface was close now, much closer than it had appeared from orbit. The descent ladder extended downward toward the grey soil, each rung a connection between human engineering and an untouched world. Armstrong moved first. His suit, pressurized and life-sustaining, carried him through the narrow hatch and onto the ladder. Every motion was deliberate, controlled, slowed slightly by the stiffness of the suit and the awareness that this environment was entirely unlike anything on Earth. Below him, the lunar surface waited. There was no wind to move dust, no sound to carry movement, only light and shadow. Each step down the ladder was a transition not just in position, but in history, a descent from a spacecraft built on Earth to a surface that had never supported life. Inside Mission Control, the world listened. Communications were steady but filled with quiet anticipation. The signal delay was small but present, a reminder that Earth was no longer immediately adjacent to this moment. Armstrong paused on the final rung. For a brief moment, there was stillness. Not hesitation, not uncertainty, just the final point between leaving and arriving. Then he stepped off. His boot made contact with the lunar soil, a small, controlled movement, one that carried no sound outward into the vacuum, only confirmation through instruments, through transmitted voice, through human awareness shared across thousands of miles. That's one small step for man. The sentence continued, carried through communication systems back to Earth. One giant leap for mankind. The words were simple, but their meaning extended far beyond their structure. For the first time in history, a human being stood on another world. Not through telescope, not through theory, but physically, presently, on the moon. He looked around. The surface was grey and textured, covered in fine dust and scattered rocks shaped by ancient impacts. The horizon curved gently in the distance. The sky above was not blue or dark in the way Earth's sky is perceived. It was black, uninterrupted, filled with stars that did not twinkle because there was no atmosphere to distort their light. Every direction was quiet. Every direction was still. Buzz Aldrin followed soon after, descending the ladder and stepping onto the surface beside Armstrong. Together, they stood in the sea of tranquility, surrounded by silence deeper than anything experienced on Earth. They moved carefully, adapting to the reduced gravity. Each step felt lighter, slower, almost floating compared to Earth's pull. The suit systems maintained life support, temperature control, and communication, allowing them to operate in an environment that would otherwise be completely hostile. They collected samples. They photographed the surface. They observed the terrain. But even these actions, while scientific in purpose, existed within a larger context that could not be separated from their meaning. Everything they did was the first time it had ever been done. Meanwhile, Michael Collins continued orbiting above, alone in the command module. He circled the moon repeatedly, passing over the landing site without seeing it directly, carrying the responsibility of return. On the surface, time moved differently, not physically, but emotionally. Minutes felt expanded. Every action carried weight. Every observation felt permanent. And yet, the moon remained unchanged. It did not acknowledge their presence. It did not respond. It simply existed as it always had, now briefly touched by human life. As the first lunar EVA continued, the reality of what had been achieved settled in slowly, not as a single moment, but as an accumulation of confirmations. The landing had worked. The systems held. The surface was stable enough to stand upon, and human beings could exist, briefly, on another world. Eventually, the time came to prepare for return to the lunar module. The first steps on the moon would not be the last actions taken there, but they would remain the beginning of everything that followed. When Armstrong and Aldrin finally turned back toward the lunar module, they carried with them more than samples or photographs. They carried evidence that the boundary once thought absolute, the Earth's surface, was not the limit of human presence. It was only the beginning of where presence could extend, and above them, the Earth hung in the sky. Small, distant, beautiful, a reminder of where they had come from, and where they would return. After the silence of the lunar surface, movement began again, carefully, deliberately. Inside the lunar module, Armstrong and Aldrin completed their surface operations with the same disciplined precision that had carried them through every phase of the mission. Samples had been collected, instruments deployed, photographs taken, each action documented not just for science, but for history. And now, it was time to leave. The moon had been touched. The mission had been fulfilled in its primary objective. But Apollo 11 was not finished, because reaching the moon was only half the journey. Returning was the other half. Inside the lunar module, systems were prepared for ascent. Unlike descent, which had required careful navigation toward an unknown surface, ascent required something equally precise but reversed, escaping the moon's gravity and rejoining the command module in orbit. There was no room for error. The lunar module ascent stage ignited, a controlled, upward push against the moon's weak gravity. Dust briefly lifted from the surface below, then settled again into stillness as the spacecraft rose. Slowly at first, then steadily, then completely separating from the lunar surface. Armstrong and Aldrin were no longer on the moon. They were leaving it behind. The view outside shifted quickly. Craters and plains dropped away beneath them, shrinking into a wide, grey expanse. The moon, which had felt immense from the surface, began to curve again into perspective. Above them, in lunar orbit, Michael Collins waited. Alone. Circling the moon in the command module, maintaining orbit with precision, monitoring systems, calculating rendezvous trajectories that had been rehearsed countless times but never attempted in reality at this scale. For Collins, the mission had been one of patience and preparation. While his crewmates walked on another world, he had remained in orbit, responsible for the integrity of the spacecraft that would bring them all home. Now, the final phase of that coordination was about to begin. The ascent stage climbed into lunar orbit. Two spacecraft, once separated, now moving toward each other again. Each maneuver calculated, each adjustment measured, each burn timed with exacting precision. In the vast emptiness of space, where no air resistance exists and motion is governed only by gravity and velocity, rendezvous is not a matter of steering in the familiar sense. It is a matter of physics alignment, of adjusting trajectories so that paths intersect at the correct moment, in the correct orientation, at the correct speed. The lunar module approached. The command module responded with controlled adjustments. Slowly, the distance between them closed. And then, after careful alignment, docking occurred. Two machines that had traveled separately, one orbiting the moon, the other landing on it, became one system again. The crew was reunited in a single spacecraft. The lunar module, having completed its purpose, would be left behind, discarded in lunar orbit, a temporary vessel that had carried humans to another world and back to its edge. Inside the command module, the mission shifted once more. Now, the focus was not landing, not exploration, but departure. The engine that would return Apollo 11 to Earth fired with controlled force, pushing the spacecraft out of lunar orbit and setting it on a trajectory home. The moon, once the destination, now began to shrink behind them. Not quickly, not dramatically, but inevitably. The grey surface receded. The craters softened into patterns. The world that had once filled their view became smaller, quieter, more distant, and then, gradually, it was no longer the primary focus. Ahead lay space again, the long journey back. But this time, something was different. They were not going outward into the unknown. They were returning from it. Inside the spacecraft, systems continued to function normally. Communication with Earth resumed. Navigation corrections were made as needed. The crew maintained their routines, but the psychological context had shifted completely. They were no longer travelers toward a distant world. They were the first humans returning from one. Behind them, the moon remained unchanged, silent, ancient, unaware of the significance assigned to it by those who had briefly stood upon it. Ahead of them, Earth began to grow again. At first, it was only a bright point in the distance, then a small disk, then a recognizable sphere, blue and white, familiar in a way nothing else in space could be. As the spacecraft continued its journey home, the scale of what had been accomplished began to settle, not as a single moment, but as a sequence of irreversible steps. Departure from Earth, landing on another world, walking on its surface, and now return. Each phase had been achieved through engineering, calculation, and coordination across thousands of people, but together they formed something larger than the sum of their parts, a demonstration that Earth was no longer the limit of human presence, only the starting point. And as Apollo 11 continued its path back, the story of the moon landing began to shift from mission to memory, a memory that would soon re-enter Earth's atmosphere, and be carried, once again, into history. The journey home from the moon was long, but not uncertain. By this point in the mission, Apollo 11 had already accomplished what it was designed to do. The landing had been successful. The surface operations had been completed. The ascent, rendezvous, and docking had all proceeded as planned. Now, the spacecraft was in a controlled trajectory back toward Earth. But even successful missions must still pass their final test. Re-entry. Inside the command module, Armstrong, Aldrin, and Collins prepared for the final phase of the mission. Systems were checked again, not because they were in doubt, but because procedures demanded it. In spaceflight, repetition is not redundancy, it is assurance. As Earth slowly grew larger in the windows, the spacecraft approached the point where it would re-enter the planet's atmosphere at extreme velocity. The command module was the only part of Apollo 11 designed to survive this moment. Everything else had already been left behind. The service module detached first, a necessary separation. It had provided propulsion, power, and life support throughout the journey, but it was no longer needed. It burned up harmlessly in the atmosphere, discarded as the capsule oriented itself for entry. Now only the command module remained. Small, compact, protected by a heat shield designed to endure temperatures that would destroy almost anything else built by human hands. The spacecraft aligned itself precisely. There was no room for deviation. The angle of entry had to be exact. Too steep, and the spacecraft would burn up. Too shallow, and it would skip off the atmosphere and return to space. There was only a narrow corridor, an engineered path back to Earth. Then, contact with the atmosphere began. At first, it was subtle, then immediate, then overwhelming. The spacecraft struck the upper layers of Earth's atmosphere at nearly 25,000 miles per hour. Friction and compression transformed the air around it into a plasma sheath, a glowing envelope of superheated gas that surrounded the capsule in silence. Inside the command module, communication was temporarily lost. The plasma interfered with radio signals, creating a period known as blackout. For several minutes, Earth had no contact with the crew. Only physics governed the descent. Outside, temperatures soared. The heat shield absorbed and deflected energy that would otherwise destroy the capsule. The spacecraft shook as it decelerated, gradually transitioning from orbital velocity to atmospheric flight. Then, slowly, communication returned. A signal, a voice. Confirmation that the spacecraft had survived the most dangerous phase of re-entry. The parachutes deployed. First the drogue chutes, stabilizing orientation. Then the main parachutes, 3 large canopies opening against the thin upper atmosphere, then fully engaging as the capsule descended more gently toward the ocean. The violent descent had become a controlled fall. The speed reduced. The ocean below grew closer. And then, finally, impact. The command module struck the surface of the Pacific Ocean with a controlled splash, rocking briefly before stabilizing upright. Silence followed. Not the silence of space, but the silence of arrival. A moment where motion ended, and Earth's gravity once again became the defining force. Recovery forces approached quickly. Helicopters circled overhead. Ships closed in on the floating capsule. Divers secured the spacecraft and prepared it for extraction. Inside, the crew waited for confirmation. They had left Earth. They had traveled to the Moon. They had walked on another world. And now they had returned. The hatch was opened. Warm ocean air entered the capsule for the first time since launch. One by one, the astronauts were lifted out, carefully, methodically, as procedures required after extended spaceflight exposure. They were placed in quarantine facilities temporarily, a precaution based on uncertainty about lunar material, though it would later be understood that no biological contamination risk existed. Still, caution remained part of the process. And then, the mission transitioned from operational to historical. Apollo 11 was complete, but its significance had only just begun to take shape, because what had been achieved was not just a landing, not just a flight, not just a sequence of engineering successes. It was a demonstration that human beings could leave their planet, reach another world, and return safely. The moon had been reached not as a distant object of observation, but as a place that could be visited, and Earth, seen from space, had been revealed not as infinite terrain, but as a single, fragile world, floating alone in the darkness. As recovery teams secured the capsule, and the astronauts began their transition back to Earth life, the broader meaning of the mission began to spread across the world. Not all at once, but gradually, like light reaching distant places after a long journey. Apollo 11 had returned, and nothing about human perspective would remain exactly the same again. After Apollo 11 returned to Earth, the mission did not end in the way most journeys do. There was no simple return to normalcy, no immediate after. Instead, there was a pause across the entire world, a collective moment of recognition that something fundamental had changed, even if daily life continued unchanged on the surface. The astronauts were safe. The spacecraft had been recovered. The mission had succeeded. But the meaning of what had happened was still unfolding. In the days following splashdown, Apollo 11 entered quarantine. This precaution, born from uncertainty rather than evidence, reflected an important aspect of early lunar exploration. Humanity had reached a place no one had ever physically accessed before, and even the possibility of unknown contamination had to be considered. Inside the isolation facility, Armstrong, Aldrin, and Collins transitioned from astronauts to living evidence of the mission. They were monitored, interviewed, and studied, not out of suspicion, but out of scientific caution and historical importance. Outside, the world reacted in waves, not all at once, but gradually, as news traveled across countries, time zones, and languages. Television broadcasts replayed the landing. Newspapers printed images of the moon's surface and the first human footprints in lunar dust. Radio stations repeated fragments of the famous words spoken on the surface. And for many people, the experience was not just about technology or competition. It was about perspective. To understand that shift, it helps to return briefly to what had been seen from space during the mission. Earthrise. That single image from Apollo 8 had already begun to reshape how people thought about their planet. But Apollo 11 gave that perspective a deeper context. It was no longer just the view of Earth from afar. It was the realization that Earth was a place that could be left behind, reached again, and observed as a single object among many. From the moon, Earth appeared small, not insignificant, but finite, a closed system floating in darkness, without visible boundaries or divisions. Borders did not appear from space. Neither did nations. Only weather systems, continents, oceans, and the thin blue line of atmosphere that made life possible. That shift in perspective became one of the most lasting outcomes of the mission, because while Apollo 11 was built as a technological and political achievement, its impact extended into something less measurable: how people saw their own world. Meanwhile, the engineering achievement itself was being carefully studied. Every stage of the mission was reviewed in detail. The launch, the translunar injection, the lunar orbit insertion, the descent, the landing, the EVA, the ascent, the rendezvous, and the return, all were analyzed to understand not just what had worked, but why it had worked so reliably under extreme conditions. Apollo was not treated as a single success, but as a sequence of systems functioning together across distance, time, and uncertainty. Each system had to perform without failure at the exact moment it was needed. And it did. But perhaps the most important lesson was not about technology alone. It was about coordination. Apollo 11 was not the product of a single invention or individual effort. It was the result of thousands of engineers, scientists, technicians, and support teams working in alignment across years of preparation. It was a system of human cooperation as much as mechanical design, and that cooperation had extended beyond borders, industries, and disciplines in a way that was rare in other fields. In that sense, the mission represented not just what humanity could build, but how it could build when focused on a shared objective. In the years that followed, Apollo 11 became a reference point, not just for space programs, but for how complex goals could be structured, tested, and achieved step by step. But at the time, in the immediate aftermath, there was also a quieter reaction. Reflection. The moon had been reached, but it had not been changed. It remained as it always had been, silent, distant, untouched except for the brief presence of human visitors. And that contrast became important, because it highlighted something essential about exploration itself. Reaching a place does not transform it. It transforms the traveler. As Apollo 11 faded from active mission status into history, the broader Apollo program continued. More missions would follow. More landings would be attempted. More experiments would be conducted. But the first step, the first human contact with another world, would remain distinct, a point in time that could not be repeated, only remembered. And in that memory, something enduring remained, the understanding that Earth is not the center of experience. It is the beginning of it. In the months that followed Apollo 11, the world did not return to what it had been before. It continued forward, of course. Cities remained busy, seasons changed, and daily life resumed its familiar rhythm. But beneath that surface continuity, something had shifted in how people understood distance, possibility, and scale. The moon landing had not altered the moon itself. It had altered the idea of what was reachable. Apollo 11 became a reference point almost immediately, not just in engineering, but in culture, education, and imagination. It appeared in textbooks, documentaries, and classrooms as a moment that marked a boundary crossing in human history. A line had been drawn. Before and after. NASA, meanwhile, did not stop. The Apollo program continued with additional missions, each building on what had been learned. Later crews would perform longer surface stays, more complex experiments, and more advanced geological surveys. The moon was no longer a single destination. It was becoming a place of repeated human activity. But Apollo 11 remained distinct, because it was the first. And firsts in exploration carry a different kind of permanence than repetition. They define the starting point from which everything else is measured. Inside NASA, engineers and scientists began to look back at the mission not only with pride, but with analysis. Every system was reviewed in detail. Every decision path was mapped. The goal was not simply to celebrate success, but to understand it deeply enough that it could be repeated safely and improved. The Saturn V rocket, the lunar module design, the navigation systems, the communication architecture, all of it became foundational knowledge for future spacecraft development. What had once been experimental became structural. But outside the technical world, Apollo 11 took on something broader. It became symbolic, not of a single nation, though it was born from one, not of a single program, though it was executed through one, but of human capability operating at scale. For many people, the most lasting image was not the launch, or even the landing, but Earth itself, seen from space. A small sphere suspended in darkness, without visible borders, without the divisions that define human geography on its surface. That image did not provide answers, but it changed the questions people asked. About environment, about resources, about fragility, about how isolated a planet can be, even when it is full of life. In the quiet aftermath of Apollo 11, some of the astronauts themselves reflected on this shift. Having seen both Earth from space and the Moon up close, their perspective was no longer limited to a single reference point. Earth was no longer simply home in the abstract sense. It was a specific, finite place within a much larger environment. A closed system, suspended in silence. And that realization would gradually influence scientific thinking, environmental awareness, and even political discussions in the years that followed. But at the time, it remained more of a feeling than a defined movement. Meanwhile, the physical remnants of Apollo 11's lunar presence remained on the Moon. The descent stage of the lunar module. Scientific instruments. Footprints pressed into dust that would not be disturbed by wind or water. On the Moon, there is no erosion in the way Earth understands it. No weather to erase marks. No atmosphere to soften edges. The traces of Apollo 11 would remain, unchanged, for a timescale far beyond human history. Silent markers of a brief visit. And in that silence, there is a kind of permanence. On Earth, the astronauts returned to public life briefly as symbols of achievement. They were honored, interviewed, and celebrated. But they also gradually stepped back into quieter roles, as the program itself moved forward to new missions. Apollo 12, Apollo 13, Apollo 14, each carried forward the work, expanding what had been proven possible. And yet, no later mission ever quite repeated the exact historical weight of the first landing. Because Apollo 11 was not just about reaching the Moon. It was about crossing a threshold that could only be crossed once. After that, the question was no longer whether humans could reach another world. It became how far they could go beyond it. And in that shift, Apollo 11 settled into its place in history, not as an endpoint, but as the beginning of a larger trajectory. A moment when the edge of the known world expanded outward, and did not return to its previous shape. In the years after Apollo 11, the Moon did not become a place of frequent human return. It remained distant, quiet, unchanged in its fundamental nature. But it was no longer unreachable. That distinction shaped everything that followed. Apollo 11 had done something irreversible in human history, not because it permanently altered the Moon, but because it permanently altered what humans believed they could do. Before the landing, the Moon was a destination of imagination, mathematics, and telescopic observation. After it, it became a place that had been physically experienced, a surface that had been walked upon, a horizon that had been seen from ground level, not just from Earth. And once that boundary had been crossed, it could not be restored. The Apollo program continued for a time after the first landing. More missions followed, each building on the technical success of Apollo 11. Longer stays, more complex scientific experiments, deeper exploration of lunar geology. The Moon gradually became less of a singular achievement and more of a developing field of study. But even as the program expanded, the cultural weight of Apollo 11 remained unique. It was the first step. And in exploration, first steps define everything that comes after. Inside NASA, Apollo's legacy became a foundation rather than an endpoint. The systems developed for the Moon landing influenced spacecraft design, mission planning, and engineering philosophy for decades. The Saturn V rocket remains one of the most powerful launch systems ever built, and its success demonstrated what coordinated large-scale engineering could accomplish when every component was aligned toward a single objective. The lunar module proved that landing and launching from another celestial body was possible. The command module demonstrated safe return from deep space. The navigation systems showed that humans could travel hundreds of thousands of miles using onboard computation and Earth-based coordination. Each of these achievements became part of a larger framework of knowledge. But beyond engineering, Apollo 11 also left a psychological and philosophical imprint. For the first time in history, humans had seen their home from the outside in a direct and unmediated way. Earth, viewed from space, did not appear as a collection of nations or divisions. It appeared as a single object, a fragile sphere suspended in darkness. That image, captured during the Apollo era, became one of the most influential visual perspectives ever recorded. It influenced environmental awareness, systems thinking, and global perspectives on shared resources. It reframed Earth not as an infinite stage for human activity, but as a limited environment within a much larger universe. And the Moon, once a symbol of distance, became a symbol of reach. Not because it was conquered in any traditional sense, but because it was visited, studied, and left as it was found. The footprints left on its surface did not represent ownership or transformation. They represented presence. Temporary, precise, and deliberate. In the broader arc of space exploration, Apollo 11 became a reference point for every mission that followed, not because it was the most complex, but because it was the first to succeed at crossing that boundary. Later achievements in space would surpass Apollo 11 in distance, duration, and technological sophistication. Space stations, robotic explorers, interplanetary probes, all would extend human reach even further. But none of them would replicate the exact historical position of that first lunar landing, because some moments in history are defined not by scale, but by transition. Apollo 11 marked the transition from Earth-bound existence to extraterrestrial capability. It established that human presence was not limited to a single world. And even though that presence beyond Earth remained rare, it was no longer theoretical. It was proven. Looking back, the mission can be understood not as an endpoint, but as a beginning of trajectory, a direction rather than a destination. From that point forward, humanity's relationship with space changed from observation to participation, from looking up to reaching out. And in that shift, Apollo 11 remains one of the clearest markers in human history, a moment when a species stepped beyond its origin and briefly stood on another world, before turning homeward again with a new understanding of its place in the universe. The Apollo 11 mission ended where all journeys to extraordinary places eventually return, not with spectacle, but with stillness. A spacecraft splashed down into the Pacific Ocean. 3 astronauts came home, and a world that had been watching, listening, and waiting slowly exhaled. But what had truly ended, and what had truly begun, were not the same thing. Apollo 11 was a mission with a defined timeline, a sequence of engineered steps, and a carefully structured return. It began with ignition, passed through Earth orbit, crossed the distance to the Moon, touched another world, and returned safely through fire and atmosphere to the ocean. On paper, it was complete. But in human understanding, it was not, because the meaning of Apollo 11 did not sit inside the mission itself. It expanded outward from it. Before Apollo 11, the Moon was a boundary, visible, familiar, but unreachable. After Apollo 11, it became a place, a real surface, a physical world where human beings had stood, worked, and returned from. That shift is difficult to overstate. It did not change the Moon. It changed the scale of everything else. Distances that once felt absolute became relative. Goals that once felt impossible became procedural. The idea of beyond Earth stopped being abstract and became operational. But perhaps the most lasting change was quieter. It came not from the engines, or the landing, or the steps taken on the lunar surface, but from the view that accompanied the entire journey. Earth, seen from space, had no borders, no lines dividing continents in visible form, no separation between nations, ideologies, or identities, only a single, finite world suspended in darkness. That image did not solve problems, but it reframed them. It introduced a perspective in which humanity could be understood as sharing one environment, one atmosphere, one fragile context of survival, and the moon, in contrast, became a reminder of what lies beyond that shared space, silent, ancient, and indifferent to human presence, yet now briefly touched by it. Apollo 11 did not end exploration. It began a new definition of it. After the mission, space was no longer a theoretical frontier. It was a navigable environment, one that could be entered, studied, and returned from using systems built on Earth. Later missions would extend that capability further. Space stations would establish continuous presence in orbit. Robotic explorers would travel to distant planets. Telescopes would look deeper into the universe than ever before. But all of it would stand on a foundation that Apollo 11 helped define. Not just technologically, but conceptually. The idea that humans are not confined to a single world. And yet, for all its scale, Apollo 11 remains remembered not for its complexity, but for its simplicity. A rocket rising, a journey across space, a landing on a silent surface, a footprint in dust that will remain unchanged for longer than any human civilization has existed, and a return home. In the end, the story of Apollo 11 is not only about reaching the moon. It is about the moment Earth became something that could be left, and then seen again from afar as a place worth returning to. A beginning disguised as a destination, a step outward that ultimately pointed back home, and a reminder that even in the vastness of space, the most significant discoveries are often not about where we go, but how it changes what we understand when we come back. Good night.